Okay, so hello everybody, and welcome to the third episode in Series 1 of the PowerShape Tips and Tricks sessions. And for this episode, we're going to be talking about model analysis tools. So the toolbar for model analysis these days looks like this. And you can see there's all sorts of wonderful tools that are on this toolbar that allow us to really understand what the CAD data is that we're working with, whether we've modeled it ourselves or whether we've received it, to understand where potential issues may lie with it, in order that we can start to think about fixing them if necessary. So on that toolbar we've got smoothness shading. This is kind of going from left to right. Undercut and accessibility shading, curvature, radius and thickness shading, comparison analysis tools, moving on to model analysis, various methods of doing that, some surface inspection, and of course wall thickness identification. So I'm going to work through all of these. My plan is to spend about half an hour doing this. Any questions that come along, I won't take them as I go. What I'll do is I'll take a look at the dashboard at the end, and if there's any I can answer there, and then I will. If not, then I'll answer those during a follow-up email. Okay, so let's make a start and let's get into a little bit of theory. So smoothness shading, it's also known as isophone shading, and what's that all about? Well, take a look at this PowerPoint slide here. When we talk about curvature matching, we talk about the mathematical term G0, 1, 2 or 3 curvature continuity. And what do we mean by that? Well, G0, what we're basically saying is one CV point is aligned. For reference, a CV point is a control vertices. So if you look at the first image here, we've got a surface on the left, or a curve on the left, and a curve on the right. And the curve on the right we'd like to try and match to the curve on the left, and we have G0 continuity. So in other words, we have a point that matches on each of those edges, and that's classed as G0. Moving on from that, we've got the next level, which is where we have two control vertices aligned, and that's known as G1 continuity. So you can see here we have 2 points in alignment. So this is positional alignment, this is tangential alignment. And looking at G2 and 3, they're of a similar nature here. If you look at G2, what we've got are effectively 3 CV points in alignment, and for G3 we've got 4 CV points in alignment. So you can think of these as not only positional and tangential, but also magnitude continuity. So we're keeping the same strength of curve on one side as we are on the other. So how does all of that correlate into PowerShape? Well, let's take a look. So here's PowerShape, and I've got a good old headlamp cavity that's been knocking around for some time now, and I'd like to just see how this is performing. So what I can do is go to this is PowerShape 2018 incidentally, go to my visualization toolbar, and I can ask for smoothness shading. And as soon as I do that, I get these kind of zebra stripes that appear on the model. So what are they telling me? Well, let's look at that C0 continuity first and foremost. How does that look? Well, this is a classic example of C0, because can you see here that from one surface to the next, the phase of these stripes from dark to light is out of phase. So the light here is butting against the dark on the other surface. And that tells me that this edge, although it shares the same edge, so it's C0, it shares nothing else. There is no tangency or magnitude continuity in this area. So that's a classic example of C0 continuity. So what about C1? What does that look like, where we have tangential continuity? Well, if I were to wander around somewhere on this model, let's pick this fillet here, for example. Can we see here that we have a dark stripe which matches into a dark stripe on the opposite surface? Now, it's a very different direction, but they match, they are in phase, and that tells me that these two surfaces are not only positionally the same, but they also share the same tangency. There's C1 continuity here, they're tangent along this edge. The fact that the curve is so different, or the shape of this is so different, tells me that that's all they are, though. There's no matching radius, if you like, no matching magnitude in this area. So let's have a look at a C2 or C3 type continuity. So take a look at this area here. And if I were to select that surface there and go for the home page, and let's just change the color in that region to something like blue. Can you see there that we have separate surfaces in here, but the curvature going from one to the other is, first of all, they share the same edge, C0, then they have the same face, C1, and they have the same curvature. I can see no difference in that from here to here, so that tells me they are C2 or above in that area there. Interestingly here, this is the same surface. I can see that it is tangential through this point, but the curvature changes drastically from one area to the next. So I can see that the magnitude has changed through this point here. So how else can we use this to help us? Well, if I look at this model here, I can start to analyze this, looking out for scenarios where maybe there was an issue that I didn't realize. So looking here, I can see that, okay, this is all tangent moving through here. That's good. They're in phase. That's good. But as I wander around this part, an alarm bell is ringing, because now I can see that here it's not in phase. Now I thought that was tangential down there, and without this tool it would not have been particularly easy for me to detect that they were not. Can you see there? That all looks good to me by eye. It's only when I isophoto or smoothness shade that I see that there are issues in that region. And of course I can then go on to use PowerShape to fix those easily. Okay, so that is the smoothness or isophoto shading. Let's undo that color change operation and move on to look at something else. So the next one I'm going to look at on the toolbar here is the undercut shading. And if I click that, what we're seeing are effectively three colors. Green means I can access it from the current axis. So Z is my current axis that I'm working on. If you imagine that's the separation axis of my part. Green is good. All of this can be separated cleanly. Yellow is a warning. It's telling me I'm approaching the minimum angle that I've specified, and red is telling me that I'm at or below the minimum angle that I've specified. So what are those angles and where do they live? Well, you can get to those these days by going to the File Options page, and on this page here you've got the Application Options, and in here we can get to the Analysis, Surface Analysis tools. If, like me, you're accessing this kind of page a lot, then what you can do is set up a shortcut, which I've done. I've got a Control W, which will open that up automatically for me. Maybe we'll talk about that in another session. So what all these values mean? Well, you can see here that at the top of the page I have undercut shading, page park, and I have the draft angle set to 0, the warning angle set to 5 degrees, and I'm aligning with my Z axis. So if we have a look at this, what we're saying is 5 degrees or above in terms of wall angle will be green, 5 degrees down to 0 degrees will be yellow, and 0 or less will be red. And that's all very useful. I can control the angle that we're looking along. I can say that it's either along the x-axis or the y-axis, and now it's looking from one of those directions for that information. Or you can say whatever the principal axis is. If you go for this option, at the bottom of the screen you can just see there are 3 coordinate systems. Whichever one of these is active is the one that we'll be working with. I'm going to fix this to Z and talk about these angles. So a little tip for you here, and the way I use this quite a lot, is if I want to know where undercuts are rather than vertical or less, what I can do here is set this value for the warning angle to be a very small value, like 0.001, for example. And then for the undercut, the draft angle, set that to be a negative value, very small, so minus 0.001. So now what we see is green for, let me just use the icon here, green for everything that we can get to that's not vertical but is accessible. Yellow is effectively vertical now, and red is undercut. So that's quite a useful way of setting this up, and I find that more informative when I'm doing this kind of work, is to know where the true undercuts are and where I would have to invoke, for example, 5-axis machining to truly machine the surface. Okay. So that's the undercut shading. Let's cancel out of there for a moment and just set this back. So how does that differ from accessibility shading? Well, let's have a look. Let's switch on the accessibility shading, and from above everything looks green. It all looks pretty much the same. From the isometric view, It all looks pretty good there. But if I was to switch on another model, and I've just randomly put a helical screw above this part, look what happens. With the accessibility shading, from above everything's green that I can see, but now I can clearly see that if I want to machine underneath this helical screw here, I'm going to need to invoke some multi-axis machining. Compare that to the undercut shading, which blissfully tells me that everything's good on this part and doesn't worry about the helical screw that's sitting above it. So fundamentally, different information that's coming through from both of these options, and both very valid and very useful. And of course, same story, this will look according to the axis that we're looking along from here. Okay, so that's the accessibility shading. Right then, now we're going to look at curvature shading. For that, I'll turn off my helical screw there, go back to a normal shaded mode of the model. Curvature shading, right, what's that all about? So, I guess we'll go to the PowerPoint first and talk about it. So curvature shading, in a nutshell, allows us to shade the model according to the radius of curvature at a point on the surface. So what is the curvature measured in? Well, it's measured in a value of 1 divided by the radius of curvature at the point that we're looking at. Now bear in mind the radius of curvature, if you think of a point on a surface, effectively there's lots of potential curvatures going through that point. If you were to rotate around the point, you know, in one direction it could be almost flat, and in another it could be highly curved. So, you know, this is the first thing to think about, is the radius of curvature at a point can vary depending on how we measure it. But we're measuring it in curvature, which is equal to 1 over the radius through that point. So what are the types of curvature we've got? Well, there's minimum curvature that we can measure at a point. Think again of that description I gave, the maximum curvature that we can measure at a particular point. The Gaussian curvature, which is the product of the two, and the mean curvature, which is the average value of the minimum and the maximum through the point. And there's also a scaling factor that we can offer, which is, okay, how are we displaying that on the screen? Are we using a very linear scale? And a little tip for you there, if you are using a linear scale, this will help identify very sudden changes in the curvature, so unexpected sudden changes will stick out considerably. Whereas a logarithmic scale, that will allow us to sort of display a wider range of curvature throughout the model. So let's have a look at how all this actually correlates to PowerShape. So let's go to our curvature shading and pop that on and get our options form up and look at the surface analysis page, which is conveniently where I'm at. And what we can see here is that at the bottom of the screen we have a page park that is curvature shading. And by default I've got this set to maximum curvature. So think of this as at any point on the part, the maximum measurable curvature value that is available through that point. Okay, and so what we're seeing here is in this area here, in either direction, if you think of a theoretical point in the middle of this face, it's a very flat face. In either direction, the maximum value would be quite a low value, because if you think the radius at this point is extremely large, then we're getting a very 1 over that value gives us a very flat curvature. If we were to look at the region down the bottom here, let's flip this for a moment and flip this over to, minimum curvature. So take a look at this fillet around here. So what we've got there is a fillet that's got a curvature value of, I'd guess it's somewhere around the 0.15, 0.16, somewhere around there. We're looking at the heat map that we've got there. How is that arrived at? Well, if we were to switch on a layer and look at this from above, what we see is that the radius in this area here, let me just minimize that off for a moment and select that radius. You can see the radius for that region is 5.8. I don't know if you can just read that off there, 5.8. So 1 over 5.8 would be a curvature of 0.17. So sure enough, 0.17 would put us on the heat map in this region around here. So remember, we're measuring off right now the minimum curvature, so the least curvature through that point. Compare that to the most amount of curvature through a point on this surface. Let's have a look at that now. We get much darker colors now, because if I were to again close this off and select this other curve going the other way, we can see that the radius there on that one is just over 2 millimeters. So again, 1/2 would be half. So on our heat map, we're going to get much warmer looking colors because the curvature here is much greater. Okay, so we can start to use that to understand what it is we're seeing on the model and how that correlates. Now at the moment, what we're looking at is very banded in its appearance, so that, there's distinct color bands going on. If I were to launch up the options page again, what I can do here is flip that from banded to spectrum. And now what we get is a much smoother transition through all the colors to help us see exactly what's occurring at all of these areas. Okay. Now there's another option that's on there. That was the mean curvature, which is the average of the two. And as I said, this is very handy. If you've got very sudden changes in local areas, this can be handy to help us spot what those conditions are, because what we'll see is where there is a sudden change, a distinct change of color from one area to the next. Likewise, for large regions of curvature, we can use Gaussian, which is the product of the two. And I can see here there's definitely something going on these fillets here. There's some anomalies going on here. So using the Gaussian, I'm able to sort of detect some anomalies on these fillets. And one of the things I find quite useful is if I were to change the representation type from spectrum to bicolor, now instead of using a full range of colors, we use one color or another to effectively denote whether it's a convex or a concave curvature. So if you look at this fillet here, what we can see is we're definitely fluctuating between a concave and convex condition on this fillet, and it's really apparent when we use the bicolor shading that that's going on. So that's kind of an alarm bell to me that that's not as smooth as I thought it was, that fillet, and I can start to go in and think about how I might smooth that region out. Likewise in this area here. So these are very useful tools to help us analyze how the part looks. Here's the linear and logarithmic that I was talking about before, incidentally. This is the page where you would select that there. So let's go back for a spectrum color, linear. So very little color change there, unless there was an alarming lump in the surface, in which case we would see it. But over the logarithmic scale, we get a more graded sort of appearance to this. The only other thing to mention is we can display the sign. At the moment, for all of these, apart from the bicolor, none of these are all effectively the modulus, the magnitude, not the positive or negative value. If we switch on the sign, you can see that we're now going into the negative as well as the positive for anything that we display. So that's an option here. Okay, so that's the curvature analysis. Let's have a look at the next one along on the menu here, which is the minimum radius shading. Pretty straightforward, this one. If I switch it on, basically everything stays in the default color for areas where the radius is greater than the value that we've specified. For areas that are the same or smaller than but are convex, we get a green color. So if you can imagine that you were having to machine this cavity, yeah, it's smaller, but a tool would still be able to fit in here. So green is used there because it's still a go. It's still okay. I could use whatever tool I've got loaded, and I'd still be able to machine this. However, the red areas where it's the same as the radius I've specified or less could be an issue, because now I need to think about putting smaller tooling in to potentially machine these areas. So again, where do we access the radius for this? Well, if I load up that options page, second page part down in this, we can see that there's a color tip radius value. So it's the tip radius of the tool, not the diameter that we're using here. So I could say actually here I've got a tip radius of 3 millimeters, effectively a diameter of 6, and everything above that would be shaded. Likewise, I could go higher, say 20, and anything less than that would be shaded to show me where potential issues would be. On the opposite side of the tool, of course, it's going to be, again, the same. Convex, concave would be red, like so. Okay, so that's the minimum tip radius shading and how you actually access the value that you've got to interpret what the numbers mean. Good. So the next one along on the tree here is thickness shading. So if I wanted to know the thickness of this, I'm going to select it and I'm going to say, okay, give me the thickness. I get an error because this only works with a solid, so not a big deal. This is all surfaces. All I'm going to do is select all of this, go to my solid page park and ask to create a solid from the selected entities. Do I want to make it watertight? No, I don't need to at this stage. I'm just analyzing with shading. Back to our visualization page, and now of course I can select this and analyze it for thickness. And what we get is, again, a kind of a heat map on the part. And we've got a minimum thickness value and a maximum thickness value, and we've got sliders that we can control these values with. So I could specify a specific value. Let's say 0.5 millimeter is the minimum. So anything in red is 0.5 millimeter or below, and 12 millimeters is my maximum. I could of course drag that to start to show areas where we're above 3 millimeters in thickness. So I'll set that to, let's say, 2 here, and then red to be less than 1. So can you see here that as we come to that knife edge on the part there, we're getting hot colors, so we're going less than 1 here, and in the areas as we come around this region here, we're getting much warmer colors. Let's go for something like 3, and that tells me that in this region here we have a thickness greater than 3 on this model. Again, that's a great visualization tool just to understand how the characteristics of the component you're looking at change and what the implications of that might be. As well as all of that on this page part, there's a Make Sections toolbar. Now this is kind of replicated with the sectioning of the model, and these tools I'll talk about in a short while, but basically they're the same as the dynamic sectioning toolkit. So I'm not going to do that right now. Okay, let's move on and take a look at a different model. For this one, I'm going to choose a blade here. This is a turbine blade. And this is triangle data. So these are this is STL model of a blade that's had some damage, and we need to think about reverse engineering this, which I've done. I've put a surface over this, just there. And what I'd like to do now is find out how good I was, how well I've kind of matched one to the other. So if I box select all of this and deselect the triangles for a moment, I just have the surfaces selected. I can go to the analysis page. You can see that immediately it tells me, well, you've already got some source items selected. You don't have any target information selected yet. So it's hovering over this. The radio box is selected here. So all I need to do is click the triangles and I get a tick for both. And what that now means is I can go and calculate what the error map would look like for this part. So between 0 and 0.2 is green here. And as I wander over the part, I get this dynamic feedback that's really useful to show me how the match is in certain areas as I wander over the part, like so. If we look at the page itself, I'll leave that there. We can first of all show statistics. So this is kind of some SPC type data, statistical process control data, that's telling us how many points we've sampled, what the mean deviation is, what the error range is from -0.9 up to 1.1 here, what the standard deviation is, and of course how the percentage of how many are below a certain amount, between a certain amount, and above a certain amount. So it gives us some useful information as to general performance, if you like, of the reverse engineering that I've done here, or the comparison. Let's be clear, I could compare one solid to another solid with this, or surfaces to a solid, or triangles to a solid. It's very, very flexible as to what is compared to what. If I want to get in and change a few of these things, I can, of course I can export the values here. So if I want to export the performance of these points, I can actually output this as an ASCII file, and what I get is an ASCII format file on the disk that has the performance information. If I look at the toolkit for this and the values as to what I can change and so on, you can see that there's a page park here under comparison analysis called error range. And by default, it's setting the error range automatically. So it looks at the minimum and the maximum and sets those to be the range. But if I'm interested in very specific range, what I could do is display either to a tolerance that I'm working to. You notice I'm working to 0.01 of a millimeter down here. So if I switch that on, immediately now you can see that the range is between plus 0.01 and minus 0.01, and I'm getting a very sort of almost binary output as to how this part is performing. What I can also do though is display the error map according to values that I want to put in. So I could say the maximum value of the error range is let's say 0.5, and the minimum value of the error range is 0.2, for example, and then we can start to see colors in between those values. And again, we can see the mean and the maximum error range at those locations. Okay, so again, useful tools here to help us control and understand what's going on with our reverse engineering part in this case. The other thing that I can do here is if I flip over to the two icons here, is I can either show it as a heat map or I can show it as kind of a linear section points. So you can see here I've got little dots on there. I'm going to just increase the scale of these so we can see. And now what we're seeing is kind of spikes at each of these locations that show us how the part is performing at each of these locations in a slightly different way. So now we're seeing kind of, yeah, as I say, surface normal spikes that show how well the part is performing at each of these locations. Okay, so that's the analysis. Let's move on and look at some of the other options that are on this page part. I'm going to go and have a look at model comparison. So I've got a part here that I've got two iterations of. One on the left called compare 1 and the other one on the right called compare 2, and I want to see how these two are performing. Well, what I could do is use the compare button that's at the top here. Now this is a very sort of mathematical comparison that goes on between the two. And what actually happens here is it looks at the surfaces themselves and looks at the XY coordinates of the point, XYZ coordinates of the points that are on the surfaces and compares those. It also can potentially compare the boundaries and the parameter curves that are on there. So a very mathematical breakdown of surfaces from one model to another. And there's the key, is it works on surfaces, not solids. So these are currently solids. So for me to flip those over, I'm going to simply select that, go to the Manage toolbar and flip that over to surfaces. Likewise on this side, Manage to surfaces. So now I have surfaces on both sides of this part. You can see here, that's a surface. Okay, so let's go through the process of comparing these. So we'll go back to our visualization page, go for our compare button. We're comparing model called compare 1 to the secondary one, which is compare 2. And if I just hit OK, what we're asking for here is an exact comparison. So we're going to compare all the points on all the surfaces to each other, as well as all the boundaries on all the surfaces to each other, as well as all the underlying parameter curves on all the surfaces to each other. So only if they are an exact match will they be selected. And can you see there that the ones that are not an exact match, so the ones that are not an exact match have been selected in the compare 1 model. So all of these differ from the left-hand side to the right-hand side. Okay, so let's undo that again, unblank. Let's try that once more. This time I'm going to go for boundaries and p-curves or none. Well, to save time, I'll just go straight to none, and I'll compare the primary side, which is compare 1, to the secondary side, which is compare 2. Now when I compare these, only the surfaces themselves are being compared, not the underlying trimming information. And fundamentally, the only surfaces that are actually different from the left to the right are these. The others must just be a variation of trimming on the surfaces. So that's all very useful. and all very mathematical, but what would be nice is a more graphical way of comparing the two. So that leads me on to the next example. So what I'm going to do is just close those off again and use my page here to reopen them. So now these are back to solids. So you can see here this is a solid on the right, left rather, and a solid on the right. So let's compare them. So we'll go back to our visualization tools. This time we'll use the second one in, which is visual difference. So if I click this button here, I'm going to compare, let's say 1 to 2, and click OK. We can of course here give a kind of a tolerance as to how much they differ by, because the fundamental difference now is this uses a shading algorithm to compare. So what we get is a really nice graphical feedback as to how this model compares. And the important point here compared to the previous example is the previous example was really very strict in how it was comparing, because you can imagine a surface that is a flat here could be a different surface style but still sharing the same space. So effectively, fundamentally, it's still the same part, but it's just modeled in a different way. And the previous example would declare those as different, whereas this technique will declare them as the same. So in many ways, this is a more friendly and usable method of comparing the models, and certainly a much more graphical way of allowing you to see exactly what's different from one to the other. And depending on which way around you've selected it, red will be material left on, blue will be material left off. And again, that's just from the standpoint of which model was selected first. To get out of that, we simply close that page, that window off. Of course, we can snapshot it and print it and so on. Once we get out of that, we're then out of the command and we're able to carry on doing what we were doing. And that leads me on to the next one of these, which is find duplicates. So find duplicates. Let's take a look at this part here. I'll just look at this one on its own for now. It was the other one actually. Let's just minimize that off. It was this one I meant to look at. And what I've done here is I've got on layer 0 a model, but I've also, to help me demonstrate this, got another one on layer 10, layer 11, and layer 12. So let's draw all of these together so we can see them. We've now actually got 4 models sitting atop each other in this area. So what I can do is use the visualization tools to go and find duplicates in a model. Now I've got the choice of saying, look, only examine the items I've got selected. So I could have pre-selected this region and said only examine these, or I can leave it like this and it will just look at the entire model and figure out for me where the potential duplicates are. Now here's the thing, if I find duplicates, do I want to select the first or the last of them? Well, I'm going to select the first in the series. So let's say there are 100 duplicates. What will happen is 99 of them, one of them will be selected and 99 will not, which allows me to then delete the ones that I don't want. So let's have a look at this. And again, we understand how this works, whether we're looking at only the untrimmed regions or whether they're trimmed as well, and whether we're comparing the boundaries or just the underlying surfaces. So when I click OK to this, you can see that what's happened here is I get a warning to say duplicate items. It's selected 3 solids and left the first of those instances alone. So now what I can happily do is hit the delete key, and 3 of those items have been deleted, leaving me with just the one that I needed. So this is a great way of just housekeeping the part to make sure there aren't any duplicates lying around before I go on to do other operations. Good. So moving on from there then, we'll quickly look at the dynamic sectioning tool. Hopefully most people have played with this and are familiar with what this does, but a couple of things I will mention is that you can change the view from not only looking along the X, Y, and the Z, but also around a specific axis. So you can now use either the front clipping plane or the rear clipping plane to click from one direction or the other and actually give step sections, should you need to, through the part. You can draw the edges. You can cap off as you do this to help see what's going on through the part as you go. What you can also do is arc fit a section if you want to take it at a specific location. I would use this button here to achieve that. But before I do, let's look at the toolkit for arc fitting. The alignment angle, what this talks about is if a section through the part is getting very close to vertical or horizontal, if it fits, if the angle fits within this amount, then it will consider it to be vertical or horizontal. So that's what this value does. If you don't want that to happen, just set it to 0. The discontinuity angle is if we see areas where there is a change in direction, but the change in direction is less than 30 degrees, again, it will consider that to be a continuous motion. And again, I can change that to be a smaller value if I don't want that to happen. And then, of course, I can control what the maximum radius is that I want to fit. So no greater than 1,000 in this case. So by controlling these values, I could control exactly what the fit criteria are for my cross-section. And again, I can control, say, look, we're going to closely match by increasing the amount of sample points that are taken. Once I've done that and I hit create cross-section, what we get is a cross-section through the part that I can use going forward. If you wanted to section at a particular location, you can of course click this button, click a point, and it will section through that point according to the criteria that I've got set. Of course, you can translucently shade from the side that you're not sectioning to see what's going on there as well. So once I click OK to this, you can see that there is the cross-section that I took with arcs fitted to it in the key locations that I requested according to the settings that I had in my dynamic sectioning page. Good. Let's unblank for a moment and go on, because we're looking at surface inspection now. So let's see what that's all about. If I pre-select, in this case, a solid, but that doesn't matter, it could be a series of surfaces I've selected, and go for the surface inspection page, what happens is, as I press the left mouse key over this model, I'm given some feedback as to some default information. The first is the draft angle. The second is the radius in one direction versus the other. So if we were to pick somewhere on this model where it's fairly clear what's going on, let's go here, for example. As I walk over this region here, the draft angle is 90, so that's flat. Onto this vertical wall, it's 0, so that's vertical. And as I wander around the radius, in one direction the radius is 2, so that tells me that the radius here is 2 going around this direction. But in the other direction, we're getting varying between 87 down to something less around here, like so. So that's very useful feedback information about the part that I can just wander over, happily gleaning information. But there's more that I can gather from this. And if I quickly do a Control W here to get my options page up, again, that's a shortcut that I've created, I can go in and I can look at the comparison analysis page, surface analysis page, and in here I can change what it is I want to show. I could show the position at a point, the surface normal, and even the wall thickness. So if I click OK to that now and select this and go for the surface inspection, you can see there's a whole raft of information here that can be displayed. Now, what's probably more useful to me if I was to go back to that and have a look at that page is probably just to show the draft angle, the wall thickness, and maybe the curvature. So I'll probably just knock these two off. Those are probably the three most useful. So again, when I inspect this, we can see that, oops, when I inspect this, we can see that I'm getting feedback about the draft angle, but can you see it's also giving me dynamically, it's giving me the feedback as to what the wall thickness is in the key areas that I'm walking around here. And it's doing that by projecting inwards until it finds something that would represent a wall thickness. Okay, so that's a very useful tool to help me analyze a part. Okay, moving on from there then, when it comes to wall thickness, if I want to be a little bit more sort of structured about it, what I can do is go to this wall thickness page here, and this takes multiple sections through the part. So very quickly, I'm going to set this to be 10 sections with a gap of 10 millimeters between each of them, and then I'm going to apply this operation. And what we see is some key values here representing the thickness at key locations on the part. I'll just try and get a view that shows that. You just see here we've got 4.45 and 8.5, so that's the minimum and the maximum being displayed here and here. And that's because I've got my minimum display being set to 1 and my maximum is being set to 10. So anything greater than 10 is ignored. It's looking for the greatest value that is less than 10 that it can show me. So if I was to set that to be, I don't know, 200 and apply now, it's the same sections, right? But this time what we see is that the largest section is down here because we've got a 196 offset down below here. And if that's something that I'm going to find useful going forwards, what I could do is create the wireframe and keep the label so that when I apply this command and cancel it, we're left behind the information that we just took. So the 196 and the 4.5 that we can use as part of a drawing or whatever it is we want to do with it. Okay, so really to finish up this session, I'm going to go with the open edges, and this really relates to solids. So here I've got a solid, and I just want to check, you know, what state is it in? How good is this solid? Who modeled it? Is it considered to be a closed solid, which can have an effect on commands going forward? If I click this button here, it tells me that to a tolerance of 0.01, this solid is considered to be watertight. Were it not watertight, and I'm going to just select a face on the top here, let's go for that region there. Let's manage that, and let's select a local face, just that one there, and extract that out. So now I've actually deleted a face off this model. Let's reanalyze that, so visualization, and we'll look to detect open edges. Immediately you can see that we have an open edge there, clearly displayed, that I can see now would be an issue if I was doing complicated solid type operations from here forwards. Okay, so that's it. That's the visualization toolkit available within PowerShape 2018. Hopefully some of that has been of use to you and has shed some light on some of the tools that are available. I'll thank you very much and say goodbye.